This is the last lecture in Chapter 10, and it presents two bonding theories that are different from the Lewis theory we've talked about so far. One of them is called the valence bond theory, and the other is called the molecular orbital theory, which you will often see called MO theory. And they both have their pros and cons. It's quite a deep conceptual lecture. It's one that may be useful jotting down some notes or printing out the PowerPoint and taking notes as you listen to it. All right, so I'm going to give just like a one-slide introduction to each of the two theories, and then I'll go more in depth. Molecular orbital theory says that two atoms that are going to bond start out with their individual atomic orbitals, and that when those atomic orbitals on each of the bonding atoms mix or combine, they make new orbitals that are called molecular orbitals. And that if we start with, let's say, two atomic orbitals, we're going to end up with the exact same number of molecular orbitals. And as always, the driving force for formation of molecular orbitals is that they are more stable at a lower energy level than the individual atomic orbitals. Now, although there were quite a few benefits of molecular orbital theory, as you'll see later in this lecture, one of the things that it does not do well is it does not predict the number of bonds all atoms will make. Carbon is a perfect example of that. If you look at the electron configuration of carbon, it has two unpaired electrons, two electrons in the p sublevel. So if you think of the boxes as orbitals, the orbital configuration would look like that. That would suggest that carbon may want to make two bonds. In fact, it makes four bonds, and that just couldn't be explained with the molecular orbital theory. So then they came up with a new theory called the valence bond theory, which honestly, as of this date, they're beginning to question that too, but it does have some benefits to it also. Valence bond theory, the whole key of that is that the atomic orbitals themselves on one atom can mix and make new hybrid orbitals before bonding, so that won't make sense in an example. So for example, let's say that we have an atom that has an s orbital and three p orbitals. Valence bond theory says that all of these individual atomic orbitals can hybridize, that is, mix together to make equivalent energy hybrid orbitals. So notice they all are the same shape. They all are identical other than the direction they're pointing in. And so those are all a result of mixing these. And you'll see as we go through them one by one that the names that the hybrid orbitals have, sp, sp2, sp3, sp3d, and sp3d2. The next several slides are going to get pretty complicated, so try to stay alert and pay attention. It can be a difficult concept. All right, so this just kind of reiterates what I already said about carbon. If you draw out the electron configuration for carbon, it would suggest that it will only make two bonds, but it actually makes four bonds. We're going to show how that can happen. Before I start making hybrid orbitals, I want you to understand some ground rules. And if you combine one s orbital with one p orbital, so 1 plus 1, you get exactly 2 hybrid orbitals. So however many orbitals you start with, you end up with the same number of hybrid orbitals. That theme stays intact with molecular orbital theory also. But notice if you have one s and one p, the hybrid orbital is called sp. Okay? Pretty simple. If you combine, on the other hand, one s orbital and two p orbitals, you get sp2 hybrids. Notice, assume there's like an exponent of 1 above the s. It's one s orbital, two p orbitals, which is exactly what they're made from. So then again, if you combine one s orbital and three p orbitals, okay, so that's one s orbital and three p orbitals, so we better end up with 4 hybrid orbitals. And we do, as a matter of fact. We'll end up with 4, and they are called sp3 hybrid orbitals, okay, because they came from one s orbital and 3 p orbitals. Hopefully that makes sense. That's rather important. All right, so we're going to go through the different types of hybrids one by one. And here's how an sp3 hybrid. Now, notice it's made from one s orbital and 3 p orbitals. Here's our s. Here's our 1, 2, 3 p's. You mix them all together, and what you get are 4 equivalent sp3s. If you put all those sp3 hybrids together, they make a tetrahedral shape. So the bottom line is, anytime you see an atom with 4 electron domains, which you know the electron domain geometry will be tetrahedral, the bond angle will be 109.5, and you can also say at this point it'll be sp3. Okay, tetrahedral means you need orbitals for 4 different locations. And sp3 has 4 orbitals. 1, 2, 3, 4. Okay, so in written summary, again, anytime you see an atom with 4 electron domains, you can say it is sp3 hybridized. The hybrid orbitals, all hybrid orbitals, are used either to make bonds or to hold lone pairs. Okay, so you can see on, this is NH3 to the right. So you can see that one of the sp3 orbitals holds a non-bonding pair, and the other 3 sp3 orbitals make the bonds with hydrogen. To show you a different way of showing you how hybridization happens, and by the way, this would make probably a perfect free response question on your next test. So it is a tough concept, but one that's important. So let's look at the orbital configuration for carbon, okay, the normal one. 2s2, 2p2, I left off the 1s2, which is down here also. Okay, but these are the valence electrons in the second energy level. The theory for valence bond theory says that in order to hybridize, one of the s electrons gets promoted to the p level, so that you have now 4 unpaired electrons. Now you can start to see how carbon would want to make 4 bonds. Okay, you've got 4 unpaired electrons. Then they hybridize, they all mix together, and you get 4 equal energy sp3 hybrid orbitals. All right, moving on to sp2. That's another type of hybrid. In life, every s sublevel has 1 orbital. Every p sublevel has 3 orbitals. Okay, but for an sp2 hybrid, we use the 1 s orbital we have, and we only use 2 out of the 3 p orbitals that are available. So that's sp2. We also have a leftover p orbital that we did not use to make our hybrids. We'll talk about what that's used for later. So sp2 hybridization gives us trigonal planar geometry. Okay, you have 3 orbitals, therefore it will adopt a trigonal planar geometry, have bond angles of 120. All right, so just word summary of sp2 hybridization. It has 3 electron domains around it, trigonal planar geometry. And as always, the hybrid orbitals are used for sigma bonds or lone pairs of electrons. What's different starting with sp2 is that we have a leftover p orbital, we'll call it non-hybridized. What is that p orbital used for? It turns out it's used for pi bonds. You may have heard the expression sigma bond and pi bond. So we're about ready to learn the difference between those two. All right, so if we look again at the orbital configuration for carbon, and we're going to do the same thing. We're going to promote one of the s electrons to the p electrons. But in this case, if we're going to make sp2 hybrid orbitals, we're only going to use 2 of the p orbitals, and that third p orbital is going to be used to make a pi bond. A pi bond is what we call, is used to make a double or a triple bond. All right, so here's the definition of the two types of orbitals. If you have direct head-to-head overlap of two orbitals, like we have right here, right in between two atoms, that is called a sigma bond. Okay, those are the strongest type of bonds. All single bonds are sigma bonds. All right, now if you have side-to-side overlap, so if you remember I said p orbitals are used to make pi bonds. If you have side-to-side overlap that's not direct overlap, that makes a pi bond. Pi bonds are not as strong, and pi bonds are used to make double and triple bonds. So if you have a double bond, one of those bonds in the double bond is a sigma bond, okay, a direct head-to-head overlap, and the other bond is always a pi bond. Okay? With a triple bond, let's take acetylene for example, one of the bonds is always a sigma bond, a head-to-head overlap of orbitals, and the other two bonds are pi bonds in a triple bond. Okay? But only in a multiple bond do you encounter p orbitals bonding and pi bonds. All right, this is pretty crazy to see this. So the bottom line is anytime you see a molecule that has a double or a triple bond, there are pi bonds involved. This is how they draw a pi bond. Okay? They're basically, the bond doesn't go directly in between the two bonding atoms. That is a sigma bond, but it kind of goes around it. Okay? So those are the pi bonds. All right, we did sp3, we did sp2, so now we're going to do sp. So sp, just like you might expect, is made from one s and one p orbital. Okay, we start with two orbitals, we end with two orbitals. Okay, and we have two p orbitals left over, okay, that we did not use to make the hybrids. So what can we say about sp hybridization? It takes place when you have a central atom with two electron domains. There's always a linear shape, 180-degree bond angle. There are two leftover p orbitals for pi bonding with sp hybridization. So here is a good example. Okay? You have a central carbon, and it has two sp hybrid orbitals. One of them was used to make the sigma bond or single bond with hydrogen, and the other one was used to make part of the triple bond with nitrogen. The leftover p orbitals were used to make the other two bonds between carbon and nitrogen to give it a triple bond. All right, now we get funky. There are two more type of hybrids, and they're weird. One of them is sp3d, and the other is sp3d2. So hopefully by now you can look at the type of hybrid and determine how many electron domains there are around an atom that has that type of hybrid orbitals. So if you can't, let's count this. There's the s makes one orbital. There are three orbitals, three p orbitals, so we have one s orbital. We have three p orbitals, and in this one we have one d orbital. So we have a total of 5 orbitals the hybrids are made from. So they will make 5 hybrid orbitals. And so this type of hybridization is for atoms that have 5 electron domains around them. If you remember, that is trigonal bipyramidal electron geometry. And the d orbitals are used to make the pi bonds. Okay, sp3d2, the last type of hybrid. That has one s orbital, it has 3 p orbitals, and it has 2 d orbitals for a total of 6 hybrid orbitals that we end up getting. So sp3d2 hybridization is used for atoms that have 6 electron domains around them. All right, here's a summary. This is probably a good thing to print out. It's a summary of the different type of hybrids that can be made. How many electron domains are associated with an atom that has that type of hybrid. Okay. So that's something that you absolutely need to know. Commit to memory. All right, so just kind of a summary of the steps you have to go through if you have to figure out hybridization. You start by drawing a Lewis structure, so if you didn't already have lots of practice drawing Lewis structures of molecules, you better start it now. Use Vesper theory to predict the geometry. Remember, that stands for valence shell, electron pair repulsion. Then that simply says valence electrons try to get as far away from each other as possible, and that's what determines the geometry of a molecule. Use a table I just showed you. It's also in your book, but I just showed you on the last slide to select the hybridization that goes along with however many electron groups are around the central atom. And yeah, you don't really need to do that. I'm not going to ask you to do that. You should be able to label the bonds as sigma. Remember, all single bonds are sigma, and pi bonds are used to make double and triple bonds. All right, valence bond theory does a lot of good things. Some of its limitations, well, these are the pros of it. Bond strengths, bond lengths. We haven't really talked about bond rigidity, but it has some pros to it. There are a couple of really important things that valence bond theory does not do, and that is properly describe what we call paramagnetic and diamagnetic properties of molecules. This is kind of obscure, but so we're going to go ahead and get started talking about molecular orbital theory. It's a good time to take a break if you want. All right, so just brief little introduction to MO theory. Schrodinger's wave equations are used to solve for the molecular orbitals, just like they were used to solve for atomic orbitals. Okay, they're obviously taking a wave into account over an area of 2 atoms rather than 1. And so the molecular orbital is considered to belong to the entire molecule, not just an individual atom. And basically, you'll see what happens is when we make molecular orbitals, we end up with lower energy molecular orbitals that are called bonding orbitals. And we also end up with some higher energy molecular orbitals that are called non-bonding orbitals. This is the crux of MO theory. All right, so when you get a bonding orbital, it increases electron density between the nuclei of 2 atoms. It's a good thing. It's lower in energy, very stable. If you get a anti-bonding or non-bonding molecular orbital, there is no good electron density in between two nuclei. Therefore, it does not promote bonding. So looking at a very simplified diagram of molecular orbitals, if you look at, let's say, two lithium atoms approaching each other, okay? Each of the lithium atoms has one valence electron. Okay, there's one over here, one over here. And the one valence electron for both of them is in a 2s orbital. The molecular orbital theory says as these two lithium atoms approach one another, the two atomic orbitals will combine to make two molecular orbitals. One of the molecular orbitals will be lower in energy and be a bonding molecular orbital. The other will be higher in energy and be an anti-bonding orbital. So any electrons that end up in an anti-bonding orbital hurt bonding. Okay? They do not promote bonding. But in the case of two lithium, you can see we only have two valence electrons to deal with. Each orbital holds two electrons, so the two valence electrons go in a bonding orbital, and this would suggest that a stable bond can be made between two lithium atoms. Molecular orbital theory gets more complicated when you introduced electrons in p sublevels. Here is the s sublevel molecular orbital formation that we just showed for lithium. Okay. Since you only start with one atomic orbital on each of the bonding atoms, you very simply get two molecular orbitals. However, with p sublevel, you start with 3 atomic orbitals on each of the two bonding atoms. So since we start with a total of 6, we have to end up with a total of 6 molecular orbitals. 1, 2, 3, 4, 5, 6. So that can get pretty complicated. Notice also that half of the molecular orbitals formed are bonding and lower energy, and the other half are anti-bonding or non-bonding and higher energy. There are two different types of configuration for molecular orbitals made from p sublevels. So in one case, the pi bond is shown lower energy, and in the other case, the sigma is shown lower energy. I wouldn't ask you to distinguish between these two. So we're going to look at probably the most common reason that molecular orbital theory is very useful, and that's distinguishing between paramagnetic versus diamagnetic molecules. First you need to know what that means. Paramagnetic means there are unpaired electrons. So the way I remember that is, it sounds like pair, but they're really unpaired, okay? Diamagnetic means the opposite. It means there are only paired valence electrons present. All right, so, and notice that we're talking about molecular oxygen here. Molecular orbital theory is the only bonding theory that can explain diamagnetic and paramagnetic behavior of oxygen. It turns out, it's really odd, but it turns out if something is paramagnetic, if it does have unpaired electrons, it actually interacts with a magnet. I mean, there really are magnetic properties to that molecule. And if it's diamagnetic, if all the electrons are paired up, it does not interact with a magnet. And so it's actually a pretty cool difference. All right, so we're going to look at the molecular orbital diagram for diatomic oxygen, which is oxygen, oxygen. So imagine two oxygen atoms getting closer together, and you have one oxygen atom on each side, okay? And oxygen, if you drew out its electron configuration, its valence electrons would be 2s2, 2p4. Okay, it has six valence electrons. Okay, both oxygen atoms do. And so here are the two s electrons. They combine to make two molecular orbitals in a sigma bond, direct head-to-head overlap. And then the four electrons that are in each of the p sublevels, you just put them in order from lowest energy to highest. And so we have a total of 8 valence electrons in the p sublevel to place. So it goes 1, 2, 3, 4, 5, 6, 7, 8, following Hund's rule, remember? So you cannot pair electrons in equal energy orbitals until each of these orbitals has at least one electron. So now we see that molecular oxygen has unpaired electrons. That's what makes it paramagnetic. It interacts with a magnet. And molecular orbital theory, again, is the only bonding theory that explains it. The last concept, a few of you made it through this weird complex lecture. The last concept I'm going to describe, and it's the last concept in Chapter 10, is bond order. Bond order, if you look it up in your book, will give you some really pretty complicated explanation or definition. And really, bond order is how many bonds are between two atoms. And so if we have something like that, you say it has a bond order of 1. If we have something that looks like that, you say it has a bond order of 2, and that has a bond order of 3. So it's really very simple. But you need to be able to identify bond orders. That'll be a question that you'll be asked. And I meant to take this out because we already talked about paramagnetic and diamagnetic. So maybe just jot this formula down. I don't think it'll make sense until I give you an example on the next slide, but it's something you should have handy. All right, so let's look at a molecular orbital diagram and predict the bond order from the diagram. So here's a case where we have nitrogen monoxide. We have nitrogen atom and an oxygen atom approaching each other. And so the valence electron for nitrogen are 2s2, 2p3, has a total of 5 valence. And of course the valence for oxygen would be 2s2, 2p4. It has 6 valence. So we have a total of 5 plus 6, or 11 valence electrons that we need to place into our molecular orbitals. And so, again, it's always easy drawing the sigma bond formation, the single bond between nitrogen and oxygen. Here is the bonding orbital. Remember, you end up with as many bonding orbitals as you end up with anti-bonding orbitals. Now, here's the deal. If these bonding electron or anti-bonding electrons weren't there, you would say it has a bond order of 1. Okay? 2 electrons make up one bond, one single bond. But anytime you have two anti-bonding electrons right above bonding electrons, they serve to cancel each other total out. So based on this bottom part of the molecular orbital diagram, there is no bond order at all. You have a complete cancellation. Okay? Moving up to the p sublevels, we have to place 3 plus 4 or 7 valence electrons up here. Okay? So that's 2, 4, 6. And nitrogen will always, by the way, unless it has a charge to it, if it's a neutral nitrogen containing molecule, there'll always be an unpaired electron. So nitrogen monoxide, first of all, is paramagnetic. Okay, so that's one thing you might be asked. It does interact with magnet. Let's figure out its bond order. So all these three orbitals are bonding orbitals. So any of them that are full contribute to a bond order. So these two electrons would give us a bond order of 1. Consider them a bond. The next two would, added together with the first one, give us a bond order of 2. This third in the bonding region would give us a bond order of 3. Okay? So far we have a bond order of 3, but now we have one single electron in an anti-bonding orbital. So for every electron you have in an anti-bonding orbital, it essentially cancels out an electron in the bonding. So this electron cancels out only one of the electrons in one of the bonding orbitals. So instead of a bond order of 3, 1, 2, 3, we have a final bond order of 2.5, because one of the electrons in this orbital are canceled. So that means that we have essentially 2.5 bonds in the nitrogen monoxide molecule. And I'm going to show you how that is actually representative of what really exists in nitrogen monoxide on the next and last slide. If we are to draw the Lewis structure of nitrogen monoxide, remember the steps. You start by counting valence electrons. Nitrogen has 5, oxygen has 6, so we have 11 valence electrons. Then you make a single bond between the atoms to start with. You give the outer atoms an octet, and both atoms are outer. I'm going to see how many electrons I've used so far. Let's see, 2, 4, 6, 8 electrons, so I can keep going. 9, 10, 11. There. I've used all the electrons I can now. I've used 11. And although oxygen has an octet, nitrogen does not. It has 1, 2, 3, 4, 5. Okay, so nitrogen is not happy. It does not have an octet. So that's when it's time to begin sharing non-bonding electrons, turning them into bonding electrons. So I'm going to take a non-bonding pair from oxygen, move it up to make a double bond between nitrogen and oxygen. I'm going to rewrite it and see if that helped the situation. Okay, so now let's count. Let's see, oxygen has 2, 4, 6, 8. Oxygen still has its octet, that's good. Nitrogen has 2, 4, 6, 7. Okay. There's no way nitrogen is going to get 8 because, and that happens with nitrogen because of its odd number of electrons. It has 7 valence electrons, 5 valence electrons, excuse me. And so it's always going to have an odd number. But I want you to look at another resonance structure of this. Okay, I'm going to take another set of non-bonding electrons from the oxygen and use them to make a triple bond between the two, just to see how that resonance structure stacks up to this one. And so what I would get then looks like this. Okay? So in order to know which one is preferred, I'd have to figure out formal charges. So I'm going to rewrite the other one down here because I made it pretty messy up there. There. Here are the two resonance structures, and let's figure out formal charges. This is all stuff you need to be able to do for your quiz on Tuesday. So let's see. 1, So oxygen normally has 6 valence electrons. In this structure it has 1, 2, 3, 4, 5. So oxygen has a +1 formal charge down here in the triple bonded one. Nitrogen normally has 5 valence. In this structure it has 1, 2, 3, 4, 5, 6. Okay, so it has a -1. And let's see how the double bonded one stacks up. Oxygen normally has 6 valence, and in this structure it has 1, 2, 3, 4, 5, 6. So it has a 0 formal charge. Nitrogen has 5, and in this structure it has 1, 2, 3, 4, 5. That also has 0. So clearly the double bond one is favored, but as it turns out, it is the real nitrogen monoxide is a hybrid of these two resonance structures. So rather than its bond order being either 2 or 3, it actually ends up being 2.5, like we found from the molecular orbital theory. And that is it for this lecture.